Hello and welcome to part 2 in this two-part tutorial on the subject of vectors. Now in the first tutorial I defined vectors and showed you some simple examples of multiplying vectors by numbers, adding and subtracting vectors. And then we looked at this very nice component representation of vectors where we describe a vector in terms of its change in x and change in y. And I showed you two different ways to represent that. So now I just want to take that forward and show you how to use that to calculate the magnitude of a vector. And then we'll generalize that to 3 dimensions as well, which is very straightforward, as you'll see. So let's actually go back to our old friend that we saw in the first tutorial. It's been very good to us, this vector A that we defined. And I indicated that vector A was 4 units in the x direction and 2 units in the y direction. So we had different ways of representing that. We could write that A is this notation for 2, which is called a column vector, or we could write it in terms of these little unit vectors I and j. I is 1 unit in the x direction, so it's 4 lots of I, and then plus 2 lots of j. J is a vector just 1 unit in the y direction. Now you can see here the way I've drawn this that we have a right angled triangle here. So the magnitude of A is obviously not going to cause us too much trouble because we can just invoke Pythagoras. And the magnitude of A, let me just write it as mag of A, we represent that mathematically as the vector A inside these 2 vertical lines. That stands for the magnitude of A, or the length of the vector A. And you can see we're going to get it straight from Pythagoras here. It's going to be the square root of 4 squared plus 2 squared. So we're going to have, for our example, that the magnitude of A is the square root of 16 plus 4 is 20. We have a nice little sort of surd thing going on here because 20 is 4 times 5. So it's the square root of 4 times the square root of 5, which is 2 root 5. Always nice to sort of reduce a surd down to its simplest form. So generally, if you're given a vector and you're asked to calculate its magnitude, you just need to take the square root of the sum of the squares of its components. So let's say someone gave us a vector C. Let's not draw it, but let's just say they said the vector was 7, negative 3, okay? And the question was calculate the magnitude. We would just straight away say the magnitude of C is the square root of 7 squared plus, and then the square of negative 3. Now the square of negative 3 is actually the same as the square of positive 3. I think it's good practice just to put the negative sign in there. Don't forget though that you are adding 2 positive quantities here, but that just reminds us that this is related to that component there. And so in this particular example then we have the square root of 49 plus 9, which is 58, I believe. 7 squared is 49, plus 9 is 58. And I'm just racking my brains to see if is there a square number lurking there, and I don't think so. It doesn't divide by 4, so probably it's best just to keep it like that actually. So this calculating the magnitude of a vector is actually relatively straightforward. Now let's generalize all of this to 3D, okay? And you'll see sort of why vectors are so powerful is that this notation and this machinery is actually generalizes straight away. And so you can start to do geometry in 3 dimensions with vectors in a very beautiful way, and that's actually explored very much in maths 1 or 2 years above this level that we're studying right now. So let me draw a vector in 3D. Let me kind of represent it in the following way. Imagine we contain this vector in 3D inside a kind of a transparent cuboid. Okay, so here's this transparent cuboid that I'm drawing. Okay, and our vector in 3D goes from here to here, and let's call it vector D. Okay, and again in 3 dimensions a vector again is just a quantity that is defined by its direction and by its magnitude. We're going to represent it here in terms of components, and let's say that that's the x direction. Let's say that this into the page is the y direction, and then let's say that that's the z direction going upwards, and let's say the dimensions of this cuboid that's just kind of there to represent the vector, let's say it's 2 units in the x direction, 3 units in the y direction, and then it's 5 units in the z direction, just for example. Well, we can represent D, this vector, just generalizing what we've got in 2D. We now have a column vector with 3 entries, x, y, and z. So we have 2 in the x, 3 in the y, and 5 in the z. And alternatively, we can write this in terms of unit vectors. Remember, we have a unit vector I that is 1 unit in the x direction. We have a unit vector j that is 1 unit in the y direction. And now we're just going to introduce a unit vector k, which is 1 unit in the z direction or z direction. And so we can represent this vector d as 2 lots of I plus 3 lots of j plus 5 lots of k. And multiplying vectors and adding vectors in 3D follows all of the same rules as we saw in 2D. So you just treat it component by component. Okay. What I wanted to just focus on here more than the arithmetic in 3D, because it tends to be the sort of thing that's asked, particularly in the Scottish curriculum, is what about the magnitude of this vector? And that's very, very straightforward. The magnitude of this vector is calculated as the square root of the sum of the squares of all 3 components. So 2 squared in this case, plus 3 squared, plus 5 squared. It's a generalization of the Pythagoras' theorem. It's very, very pretty, and you see it's the simplest possible generalization. It's literally the square root of the sum of the squares. It's just that we have 3 objects that are being added here because we have 3 dimensions to our vector. So let's just do the arithmetic here then. So we have the square root of 4 plus 9 plus 25, which is the square root of 25 plus 9 is 34, 38. I seem to be on a roll here of not having square numbers as factors, because I don't think that that surd can be simplified either. Sorry about that. Never mind. Nothing wrong with the square root of 38. That's a fine surd. So you might ask, why is that generalization of Pythagoras' theorem correct? And let me try and sketch that. And I think I have another coloured pen hanging around. It's actually quite nice. Do you see in this cuboid that if I draw a diagonal from here to here, that we have a right angle triangle? And it's sort of like a yacht sail cutting across the cuboid here. And so we know that the square of the hypotenuse, d squared, would be 5 squared plus this diagonal squared. But this diagonal is just the hypotenuse of this triangle here in the xy direction. So we actually have two right-angled triangles kind of making up this figure. So the diagonal in the xy plane we can get from Pythagoras in that 2-dimension, and then in this kind of yacht sail slice we can use that hypotenuse as a side now in this triangle, and this squared plus this squared will be the thing that we want, the square of the magnitude of d, and therefore you see that this length squared plus this length squared plus this length squared ultimately gives us d squared. So that generalization of Pythagoras to 3D really comes about because of this very nice little bit of geometry here. So I'm going to leave 3D vectors there. They're not really studied that much at this level of maths, but I think you are expected to know that they exist and how to represent them and how to calculate their magnitude. The last topic in this vectors subject is something called position vectors. Remember I said that the vector A was not defined by where it is, it's just defined by its magnitude and its direction. So we could draw an A sort of nearby and it's the same vector A. Position vectors are vectors in terms of the way we represent them, and they have a direction and they have a magnitude, but we do actually sort of limit their freedom. We basically tie them to the origin of a coordinate system. So let me do this in 2 dimensions. Let me draw some coordinate axes here. Okay, so here's x and y. Here's my origin. And now what's sort of happening is that vectors, the topic of vectors is kind of hitting some of the things we talked about in earlier tutorials around sort of drawing graphs and so on, because all of a sudden we have x and y and we can talk about coordinates. So I could have a point here, let me call it a point A, and let's say its coordinates are 1, 5, say, okay. I can have a point B, say over here. Let's say its coordinates are, say, 4, 2, just for example, okay? And that's fine, there's no problem. But actually, it's quite helpful to draw an arrow from the origin to these points. So here's an arrow connecting the origin to A, and here's an arrow connecting the origin to B. Why not label those arrows with a vector symbol? Let's call that A, a vector, not to be confused with our old friend actually. So in fact, I'm tempted to, yes, I think I will, although this is a bit messy and I apologize. I'll tell you what, I'll call them A tilde and B tilde so we don't confuse them with our old friends A and B from the last tutorial. So I'm going to call this vector, I'm going to put a little symbol on top called a tilde just to say that it's not that vector A over there, because I don't want to confuse you with using the same symbol for 2 different things. And here's a vector B tilde. Okay. So we have these vectors now that connect the origin to these points. And what's nice about these position vectors, which are defined relative to the origin, is that their vector form, if I write that vector we're calling A tilde down, it's just the coordinates of this point directly tell me the vector. It's 1 in the x and 5 in the y. So I could write that, for example, as 1, 5, or alternatively I can write that as I plus 5j, and this vector b I can write as 4, 2, or I can write it as 4i plus 2j. Okay, just using the 2 different notations for components there just to give you helpful practice. So we could now have a very nice way of describing a line segment. There is a line that we can connect from A tilde to B tilde. Okay, let me give that an arrow, why not? All right, and when we connect points, we often use the location of the points and we just write them together. We say AB is this segment here, and we might draw an arrow above it to indicate that that's a vector. All right. I'm really sorry. I'm going to get rid of the tildes above those coordinate points there because it's just getting too messy. So A and B are these points. AB with an arrow above them is the vector that goes from A to B. And we can do a little journey now. We can say, well, how do I get from A to B? Well, I can go from A down to the origin, so I can describe that as AO, and then I go from the origin up to B, for example, OB. Okay? And going from A to O is the opposite from going from O to A, so I can write that as the negative of OA plus OB. And what I'm doing here is in fact writing vector arithmetic, because OA is literally our vector A tilde and OB is our vector B tilde. So what I've written here effectively is minus A tilde plus B tilde. So this vector that goes from A to B, I'd rather write it as B take away A, in fact. We can get directly from our vector component forms here. So the vector of the line segment A to B, we can write as B tilde for 2, say, take away A tilde, 1, 5. And all of a sudden we have a very nice simple vector form for this line segment. Remember, when we do arithmetic with these component representations, we just treat x or y components separately. So looking at the x components, I have 4, take away 1 is 3. Looking at the y components, I have 2, take away 5 is negative 3. And so 3, negative 3 is the vector representing AB. We could ask, what is its magnitude? What's the magnitude of that vector AB? And we would just take the square root of the sum of the squares. So it's 3 squared plus the square of negative 3, which is the square root of 18. Alternatively, we can think of this as 3 root 2. Okay, so that would be the magnitude of that vector. One last thing, I suppose. I mean, you could imagine a slightly trickier question, which is the following. They could say a point C is 1/3 of the way along this line segment. What are the coordinates of C? And using vectors for that would be very simple, because we're effectively being asked the vector OC, in fact. So we can write that the vector OC is, first of all, go to A. I could go to B, but let me just go to A. And then I'm told that it's 1/3 of the way along. And so it would be 1/3 of the vector that we've calculated, AB. Okay. So we then have the vector OA, which is our vector A, which is 1, 5, plus 1/3 of the vector AB, which we've calculated here, 3, negative 3, which is, we just shift the paper up here slightly, 1, 5 plus remember, when we multiply a vector by a number, we just multiply each component separately. So 1/3 times 3 is 1, and 1/3 times negative 3 is negative 1. Then we can add these two vectors together, and we get 1 plus 1 is 2, and 5 take away 1 is 4. 2, 4. So 2, 4 would be the position vector pointing to C. We can just call that little c. Or to be consistent with my rather ugly notation, but C tilde, just to be consistent, is 2, 4. And that at the same time is the set of coordinates of that point C. So I hope that's been helpful. I apologize for that tilde notation, but I didn't want to confuse you with the same symbols. I do notice actually in some exam questions they sort of use symbols rather too much. They always use A and B for things actually, and it can get rather confusing because they seem to be standing for many things at the same time, so I didn't want to repeat that confusion. So just to recap this tutorial then, we looked at our old friend vector A without the tilde, the different notations for the components, and we showed that it's just Pythagoras to work out the magnitude, so it's very straightforward from the components to work out the magnitude of a vector, just the square root of the sum of the squares. We did another example. We generalized this to 3 dimensions, and it just generalizes beautifully, so really almost nothing to say there really. You just add another component on, and the magnitude is calculated from, again, the square root of the sum of the squares of the 3 components. And the final topic was looking at position vectors, where we essentially tie vectors to the origin to then point to coordinates in a coordinate system. And that's a very helpful way to sort of quickly do essentially geometry in a plane. So here we were able to quickly talk about this line segment. We could represent it as a vector. We could talk about a point that lay on that line sector very straightforwardly, just by manipulating vectors. All this could be done without vectors, but vectors just provide a very natural language, and particularly if you're in 3 dimensions, they really come into their own, because I can tell you doing 3D geometry without vectors is no fun at all, but with vectors it suddenly becomes a breeze. So with that, I'm going to say farewell to the topic of vectors. I hope it's been helpful. I hope it hasn't been a bit too quick. I do feel maybe I've skirted over things rather rapidly, but again, you'll have many other resources to use alongside these tutorials, and as ever, I do earnestly hope that they have been helpful, and I'll welcome your feedback if you see there are ways that this could improve. So with that, one last topic, statistics, and I'll see you next time.